successful one. The week has been going smoothly. I want to say a big congratulations to us who have scaled through the first month of the training. It was very tough. But Oluwa dey involved. So we are going to enter the second month, and I want to say it that this second month, this from now, this phase we are entering is very delicate one. That the only thing that can make you perfect is practice. So if you don't practice at these sessions, you will get it lost. We have been doing a lot of introduction to chemoinformatics, to computational chemistry, and we have covered a lot. I'm here to receive my assignment on nanoparticles, but I no go talk anything, sha. Make I just do my day.
My boss, that assignment, I didn't see anything to my email. Because you said that you will send it to emails now. I have not seen anything.
No, it was not sent to email. It was in the group chat.
The group chat? Hey.
You dey read message for our group chat?
I know they read though.
Nah.
Read.
Because no be woman send and give you now.
Wahala there. Wahala there.
I understand.
I don't know. Maybe I will check it. I will check it out.
I understand. So quickly we shall look at. Let me share my screen. We shall be looking at chemoinformatics. Chemoinformatics is a very bright area. Please, at this point, if your mic is on, I would like you to off your mic. Yeah, if your mic is on, you can do it to off your mic. All right, are you seeing my screen?
Yes, I can see your screen.
Okay, sir. Welcome, sir. Good evening.
Good evening.
So, henceforth, for our classes, we shall be using one link for all the classes, both the first session and the second session. So once this session ends, we are going to be joined with the same link. Okay, so once this session ends, we'll use that same link and rejoin for the next session. So all our classes, I will not be sending link again. We shall be using this one link for all our classes. And then I will not be sending link again for video. After this class, I will send the link for this video. The next classes will be using the same link for this video to access other videos. I don't know if you get what I'm saying. It's just like a folder. So multiple video link is, I see it as too ambiguous. So what we'll do is, after this class, I will send the video of this class with the link. But next classes, I will not be sending links again for the video. All the video will be on this link. So what you just do is to come back to the link of today's video and click on the link. You will see the updated videos. So all the videos will be updating by itself, so that they will be in one folder in your Google file. That is how we want to do it. And they will be using one link. So one link for our classes from now to the end of the class, and one link for our materials, for our videos and materials. So far,
Sharp.
Very
sharp.
Yeah. So far, I want to say thank you for coming around to Chemoinformatics. Before I continue, do anyone have idea on what this course is all about? Have you heard it before? Is it your first time? When you heard it, what do you think? What do you think it's all about? If it's your first time, no problem too. If you have not heard it for the first time, that means you have an idea. Let's share it. Now they think
No, we know they think we don't hear am before. The first time I actually heard about Chemoinformatics it was I don't know if I saw it somewhere, but from the statement itself, it would show that it involves chemical and maybe like information on chemicals. So but there was no expansive knowledge of it. But from the like looking at the name, you could easily say, okay, this is somewhere that you can get information about chemicals.
Oh, that is a brilliant idea, and that is just the idea. That is just the idea. We are done with structural representations, optimizations, and modeling. The next thing is, how can we get informations that are related to our chemical structures? So chemoinformatics is all about retrieving, sourcing, looking out for any kind of information regarding to your chemical structure. That is chemoinformatics. So at the end of this course, you are going to be able to learn how to retrieve any mark my sentence, or mark the words or the phrase, any kind of information that is related to a chemical structure. So doing the goal of this course is to provide solid foundational and practical knowledge in chemoinformatics using non-machine learning based tools for compound screening, structural analysis, and early stage drug discovery. All those ones are minor. The course is divided into 4 modules. The first module involves foundations of chemoinformatics and structural representation. We talk about the introduction to chemoinformatics, chemical structure representation, structural file format and conversion, chemical databases and data retrieval. Then module 2 shall look at descriptors, fingerprint and similarity analysis, which will involve molecular descriptors, fingerprint and feature representation, chemical similarities analysis, clustering and visualization of compound libraries. Then module 3 we shall look at QSAR, quantitative structure activity relationship. I have been mentioning this always. We shall look at the introduction to QSAR. We shall look at data set preparation and creation, classical QSAR modeling. We shall look at model validation and evaluation. At the module 4, the final stage, we shall then look at ADMET, draw likeness and project work. So let us get ready. It will be an interesting journey. Quickly, I want to start. So just like I have done the foundation, we will start by looking at the basis of chemoinformatics, what chemoinformatics is all about, what do I stand to gain from this course. Like as I have said, what is chemoinformatics? Chemoinformatics, also spelled like chemoinformatics. If you look at it, there are 2 words there, chemo and information. So the chemical information. So it is an interdisciplinary field that combines chemistry, computer science, mathematics, and information technology to solve chemical problems using computational tools. I have to explain this. This course is all about using the knowledge of computer science and mathematics. So this course is all about using the knowledge of computer science and mathematics to retrieve informations that are related to a chemical compound. That is the summary of what it is. It is the use of computer science and mathematics to retrieve informations that are peculiar to a chemical structure. So it is still part of the computational tools because you are using softwares, programs, web servers that has been developed and built by people. Most of the tools we use in chemoinformatics are database. These database are depositories of chemical informations related to a compound. And like I said, I made mention that in chemoinformatics you can retrieve any kind of information that are peculiar to any compound. Any kind of information of your in your mind, you can get their chemical properties, you can get their physical properties, you can get their biological properties, the kind of disease they can attack, where I can use them, the kind of conditions they can be subjected to, any kind of information you want to know about a compound, you get it from chemoinformatics. Now those informations has been gathered by some organizations sponsored by some countries. They gather these informations and store it in a database. So it will now become easier for us to go to those databases and retrieve the information. Some of them are not just stored in the database, but some of them uses computer programs to generate information about a structure. So once you put the structure, once you put the chemical identity of that structure, like the SMILE code, I told you earlier that SMILE code is a chemical identity. Please, if your mic is on, you can help me off the mic. So once you put in the chemical identity of your structure, some of this database does not have deposited informations. Some of the informations is being generated by the structure you input. So once you input the structure, based on the chemical properties of that structure, it will generate some kinds of information that you may need. Without you going to the lab to evaluate those data. So it saves cost and saves time. Let's say, for instance, people has been saying that manganese is toxic. This our star manganese is toxic and all those stuffs. Do you know that I can get informations of if the star manganese is always is really toxic or not, without me conducting any toxicity experiment? All what I need to do is to characterize the manganese, look out for the ingredients that we are using making that star manganese. Because in chemoinformatics, one thing that you must have is the chemical substance. Once you lay hands on the chemical substance, then you can use the chemoinformatics tools to get any information of your choice. So since I want to get information about the toxicity of this star manganese is not a compound, is not a chemical. So whatever effect it will create, it must be as a result of the additives, the components used in making such products. So what I will just need to do is to lay my hands on the on the chemical compositions of that of that product. Once I lay my hands on that and identify chemical A, chemical B, chemical C, I can use chemoinformatics to get information on the toxicity profile of each of the compounds present in that product. These toxicity profiles, if you want to examine them in a lab using in vivo by animal model, it will cost you so much. I can know if compound A is toxic to the liver, to the kidney, to the eye, to cancer. Does it cause cancer? Does it cause eye irritation? Does it cause whatever? I can get this information from chemoinformatics. So any kind of information, you can get it from chemoinformatics. Okay, let's say for instance, I have a compound, let's say aspirin. Aspirin has been known to be a pain relief. Do you know that with chemoinformatics, I can also decide to ask myself, apart from inflammation, what other pharmacological properties can aspirin possess? Apart from acting as a pain relief, what other pharmacodynamic properties can aspirin possess? I can use my chemoinformatics and predict all the disease targets of aspirin. Let's say you have built a nanoparticle, for instance, and you don't want to do a blind work, you don't want to do any trial by error. You want to ask yourself, what kind of disease can this my nanoparticle attack? What kind of disease can it be used to treat? I can use chemoinformatics to find out all the possible targets in the body that this my nanoparticle can attack without me doing trial by error. So any kind of information of your choice can be gotten through chemoinformatics. I've told you that there are two types. There are ones that the informations we are already deposited online. So those ones that we are deposited online, if you kill in what is not there, it will not give you any results, because it's working based on garbage in, garbage out. But there are ones that works with the computer programs, that nothing is actually deposited in that server, but the server has been programmed to understand the chemical properties of any structure that is being inputted inside the software or database. So what you need to do is to put in the chemical identity of that your structure. It will build an algorithm and develop all the informations of that structure. Once again, welcome to Chemoinformatics. Chemoinformatics plays a critical role in drug discovery. Not only in drug discovery, because I was teaching the students on Saturday, my physical students. Unfortunately, my major area is drug design and synthesis, though not limited to that area. So they were now asking me, sir, every time we have been mentioning drug design. Some of us here, we are not organic chemists. We are not in organic chemistry. So please diversify. I had to now diversify. So it is not only limited to drug discovery, but we can apply it in material science. Remember, I did not mention information about drugs, but I mentioned information about any chemical that in your mind. You can get those information. So it has a role to play in material science. Of course, material science is a cutting-edge science that also cuts across engineering. It can be applied in environmental chemistry, it can be applied in agrochemistry, among others. Currently, NAFDAC has withdrawn paraquat, right? Paraquat. Paraquat has been is a herbicide. Suppose use it as insecticide. This paraquat was discovered, and they found out that the chemicals used in making this paraquat can reside in soils when used as a herbicide. After killing those plants, it can reside in the soil. It can bioaccumulate in the soil for a long period of time. And when you plant another crops there, those crops absorbs this chemical component in form of nutrient through the xylem cells and store it in the plant parts. And when eating, they also form residues. They reside in the human body over a long period of time, causes some adverse health effects. I was now asking myself, didn't NAFDAC analyze these products before approval? I came up with an answer that this monitoring team cannot analyze all toxic properties of a compound. They will only analyze the ones that are peculiar to them. Why? Because it is not possible that you can conduct all toxicity. It's not possible in a lab. But with the help of these chemoinformatics tools, you cannot get any information you want to get from your compound. That is the beauty of chemoinformatics. Now, chemoinformatics involves several aspects. One, it involves storage. You know, I'm actually afraid of also, and they fear us, because we are entering a very delicate part that we shall embark on a project. Let me say it now. Before, at the end of chemoinformatics, before we move into molecular docking, we shall embark on a project of building database. So it involves storage. What are you storing? You are going to store chemical informations about your chemical structures. So the first thing is to store. These things are found online as database. So the first thing you do is to store informations. Just like me, as I am a computational chemist, I have my personal database where I have stored ready to use chemical structures. So I won't like, if I want to use them again, I will not be going back to the source and start downloading them. I can just go to my own database where I have stored information about my ready to use chemical structures, and the work will be easier for me. So you store informations. What kind of informations can you store? Any kind of informations. We can build some compounds, model them, and begin to source for their informations, their physical properties, their chemical properties, their biological properties. These three basic informations, we can start to say, okay, let us store like 50 chemical properties, 50 physical properties, 50 biological properties. By the time we get for each compound all these properties, we can then store them. That compound A, once you click on compound A, you will now see all the 50 physical properties we have stored. If you want to get information on the chemical properties, you look at the chemical properties. We have seen how to get some of these properties from ChemDraw, where once you draw a structure, you can go to analysis window or chemical properties, and it will run down some of the properties of that your compound. So you now store them. Our aim, our vision is, at the end of this class, we can build a database online. We can build a little website, a little database, and host it online. So it will be a collaborative work. that this set built a database. Glory be to God. One of us in our midst is into web design, so he can help us and build that little site for us where we can have our own database. Nigeria as a whole does not have a database of phytochemicals. So we don't have a database of phytochemicals in Nigeria. The US has a database. India has a database. How did they got this information? All of you who want to publish work, you like publishing work in a international journal, you are giving them your data. You will struggle to have a result of your project work, your research work. You say you are looking for high impact journals. You don't want local content. We are always giving our work. Europe, Britain, England, Brazil, India. We will send our work to them. All because we want a high impact journal. Scopus Index, Elsevier. Now what they do is that they will accumulate all these results we are sending to them and create database which will start paying to access. So we now will start paying to access our own information. So the first step is storing of your data, then indexing the data. You give the data an index, a code. You provide a code for that data. You provide a code for the data. The code might say, okay, instead of writing the compound name, you give it a code. Maybe we have paracetamol. We can say, okay, let paracetamol be PP1, or we can say let our database be PZ. So we have PZ001, PZ002, just like how all our students in our department have their arranged numbers. That is their index. So just the way you create a result sheet, what you are doing is you are creating a database. It also involves search. So create a platform for searching where you can now key in the index of a given compound. Once you put the index, maybe PZ001, the information about PZ001 is going to pop out. So these are the things that make up a chemoinformatics database. It has storage of data index, search, then retrieval. It gives you the platform after searching to also download, to retrieve what has been deposited on that database. These are the characteristics, features of every chemoinformatics: storage data, data index, a search platform, and a retriever, and easy to retrieve. You can easily download structures from there. Then analysis of chemical data. Having retrieved these data, you can then use them to perform your chemical analysis. It all depends on the researcher's interest. Then we now look at the key areas of chemoinformatics. The key areas of chemoinformatics. So sorry, what I'm doing is I'm giving you foundational knowledge. But meanwhile, if you have a question, please don't wait till the end now. Just go ahead and speak so that the class will be interactive. So before I look at the key areas, does anybody have a question to ask? Maybe a thought, something has entered your mind. Can you express? Hello? Hello. Okay, no question.
Okay, we see there.
And do you have a question to ask so far?
Hello, we are still here.
Any
We are
question?
with you.
Okay, all
Yeah,
right.
we can hear you.
So we shall look at key areas of chemoinformatics. One of the key areas is molecular representation. With chemoinformatics, you can represent your molecules in any form. You can represent your molecule in 2D and 3D. So when we look at this database, you will see where you can download these molecules in their 2D or 3D. You can download the structures. Some of us have heard about PubChem. I think I've also showed PubChem. PubChem is one of the most commonly used deposited database. So it gives you an opportunity to represent your structure of any kinds. You can represent them in 2D or 3D using your chemical drawing tools like ChemDraw. You draw them and upload in that site. You can also represent the structures in any file formats. So structures in chemoinformatics are represented in different file formats. We have the SMICE, the SMICE code, we have the inch code, the mole, the SDF. When we are using ChemDraw, we are exposed to how we can save our structures as structural data files. You can decide to also save the structures in other formats. If you look at those ChemDraw and those ChemSketch, it enables you to save your structures in different file formats. So we can build a database where we can save our structures that have been drawn with ChemDraw. We can now save it as mole, as mode 2, as SDF, as PDB, as PDBQT. So anyone who wishes to download can now download any one of their choice depending on the language the software they are using can interpret. There are some softwares that operate on PDB. Some softwares operate on SDF. So you now download the one of your interest. These are all under molecular representation. We can also represent our molecule using chemical descriptors. In chemical descriptors, it involves using numerical representations of chemical features, whereby we can provide the molar weight of our compound, the log P, the number of hydrogen bond donor, the number of hydrogen bond acceptors, the number of rotatable hydrogen bonds, the number of flexibility. We can provide such kind of information, the solubility value. We can provide the density. We can provide the molar refractometer. We can provide the mass to charge ratio. We can provide the TPSA, the topological polar surface area value. All these are chemical descriptors. They are numerical representation of your data. The values, chemical values that are used to represent your data, like the molar mass, the density, all these are called chemical descriptors. So we can also use them, and they are all found in database. All these database usually composed of these three things. So these are the three ways you can represent your molecule in chemoinformatics. You draw the 2D and 3D structures, save in various file formats, and then provide a lot of chemical descriptors. It can be physical descriptors, physical parameters, chemical parameters, or biological parameters. That is for the chemical representation. Another key area is database management. This is very important. When you have been able to represent your molecules, you now see how you can manage this database. So already you now store them and manage. You now store those files in a database. An example of this database are PubChem and KBL.
Okay, understand.
PubChem and KBL are two major chemoinformatics database that every computational chemist must be well familiarized with. So these two are two major chemoinformatics database that every chemoinformatics student must be well familiar with. So at this point now, you now build a system that accommodates all the informations where you can store and then manage them. You can also have a platform where you can search. Now in chemoinformatics, we have different types of search. We have exact match, we have substructure, we have similarity search. So we can give room for different kinds of search. Let me explain what these kinds of search mean. Exact match means that maybe I'm searching for aspirin and I type aspirin. Means if I go for exact match, it means I want to get only aspirin. I want it to get to pop out as only aspirin. Like I want informations on just aspirin. That is for exact match. So some of these database can provide informations on exact match. But you can say, okay, I don't want aspirin, no, even though I typed aspirin, but I want to get information on substructures of aspirin. I want to get information on substructures of aspirin. What is these substructures? Substructures will provide informations of compounds that contain the same backbone of aspirin. Okay, though, we have substructures, we have superstructures. Okay, yes. Substructures will provide informations on the same backbone of aspirin. Let's say that what make up the aspirin is
you said backbone.
Yes, the same
back.
Back.
Is it back?
The same backbone, like the scaffold. Like aspirin contains a benzene that has a carboxylic acid group and an acetyl group. So, okay, I want to get informations of structures that has a benzene and a carboxylic acid group. Like, let me come in from the last two assignments we did. We modeled some derivatives. Some persons were modeling derivatives of quinoline. Now you can say, okay, let me do a substructure of quinoline, meaning that I want to get compounds that are derivatives of quinoline, which is compounds that will maintain that quinoline but with different substituents. You can get them from this database depending on the type of search you want. We have exact match, we have substructure, we have similarity search. Here the similarity search is compounds that has similar substituents with that of aspirin. That is similarity search. Compounds that have similar appearance with aspirin. This similarity search may not give you compounds that have the same scaffold with aspirin, but it will give you compounds that are similar. Probably two benzene group with carboxylic acid or one benzene group with carboxylic acid. Most times the compounds in similarity search may not really have most things in common, but what it does is that it will look something that this one has and another one has it will bring it up for you. maybe since aspirin has an acetyl group, if you go for similarity search, it will also bring out compounds that has acetyl group as well. And since aspirin has a carboxylic acid group, if you go for similarity search, it will also bring compounds that has carboxylic acid group, compounds that has acetyl group. In fact, compounds that has anything similar to aspirin. That is what you will get from similarity search. We have the fourth one called superstructure or structure. That one is not really relevant. What superstructure does is that it will break that aspirin down. It will break the aspirin and begin to give you fragments. It will provide fragment of aspirin, those small molecules that make up aspirin. It will bring them out as superstructure. It all depends on what is your interest. What are you searching for? What kind of structure are you searching for? Are you searching for information on only that your compound? So it all depends. And I think I'm going to tell you, when do you search for exact match? When do you go for substructure? When do you go for similarity search? Let me just wrap it off. You go for exact match when you want to get information peculiar to that compound. But let's say, for instance, I want to develop a drug. I want to see if compounds that have the same derivatives, so compounds that were derived from the same source, I want to see if these compounds will have similar properties. That means I will just type maybe quinine, and I want to get structures that have the same scaffold with the quinine. So because of my interest, I want to know if compounds that have the same scaffold with the quinine, if they will share similar activity. So what I will just do is to look for substructure. Substructure will give you structures that have the same scaffold or backbone without a compound of interest. So as we proceed, we will begin to learn how to search for all this kind of data. Another key area is modeling.
Sorry, sir. Question.
Yeah. Oh, okay.
The superstructure, is it superstructure or suprastructure? Which one?
Okay, it depends on what you see in the database. Some uses supra, S-U-P-R-A. Some uses
PR, that's supra.
Yeah, that is supra. Some uses S-U-P-E-R. But whichever one you see,
okay,
they are all pointing at fragmentation structures. Fragments that make up that bulk structure of your interest. Like aspirin now, if I break aspirin, I will have a ketone. I can have a ketone from aspirin. I can have benzene. I can have an acetic acid from aspirin. So what those superstructure does is to break the fragments that can make up that your structure. All right, are you cleared?
Yes. I was thinking it was supramolecules, like supramolecules.
Okay, let me just show
That's
you.
what I was thinking.
Okay, let me just show you. Let's go to PubChem. Let's see something from there. Let's go to PubChem. We just pray the network will be fair with us on this PubChem. Sometimes it takes time to load. Okay, let's continue. Once it opens, I will use that to show you what I really mean by those kinds of search. Okay, it's coming up. All right, now let me search atenolol let me just use any compound. Yeah, you better be careful now. Sorry, it's still loading, so let's just wait a while. Okay, let me say I want to type atenolol, and I search. Now this is PubChem. PubChem does not work with algorithm. It works with already deposited.
They have timed also. In the next 11 minutes.
Next 11 minutes.
Time will be up.
Okay, let me just use this time and wrap it up. Now, here you can see. Are you sure what is here? What is this one? Best match, right? Can you see the screen? Are you seeing my screen? Oh my God. So, well, this is best match. So, what came out first is the best match. That is exact match. So, what will pop out first is your exact match. Now, do you want to get other informations on the similar structure? So, do you want similar structure? What you just need to do is you can come to similar structure and click on similar structure. Once you click on similar structure, then what kind of similar structure do you want? I don't know if you are seeing my screen. Hello? Are you with me? Oh. Can you all hear me?
Your network is breaking, oh.
Okay, but can you hear me now?
Network is breaking. We have 9 minutes.
Okay. But can you hear me?
Yeah, we can
Yes,
see
we
screen
can
now.
Okay.
We are seeing it, but the network is breaking.
Okay, sorry.
We can see it,
Yeah,
sir, but
we
the
can
network
see your
is breaking so
Okay.
bad.
Okay, let me use the 9 minutes to wrap up what I was meaning, what I...
Okay,
It's okay now, you can go on.
I don't know whether am I the only person experiencing it.
Okay, let me use this 9 minutes to explain about this search of a thing. When I typed, let me go back. When I typed atenolol, the first thing that came up is for best match, which is exact match.